Hi, welcome back to Chapter 13, Part 2. In this second part of our lecture on nuclear physics, we will be looking at radioactivity, fission, and fusion. We left off in Part 1 of this lecture talking about the stability of the atomic nucleus. And the main point was that the stability of the nucleus requires a very delicate balance between the number of protons and neutrons. And if we don't have the correct number of protons and neutrons, the nucleus becomes unstable. And what happens with an unstable nucleus is it becomes radioactive, and it will undergo a process called radioactivity, in which it lets off radiation, and it eventually tries to stabilize itself. And I won't go into the details of this graph again, but basically there's just a thin region of stability, which are all the blue data points shown here. There are about 250 stable isotopes of all the various elements. And notice that the region of stability is very narrow on this graph. It's just a thin stripe. If you're outside of this region, you're in the red regions here, and there are over 1,000 unstable isotopes, and these are radioactive. So we're going to look at what radioactivity is, and that'll be the main topic of this lecture. We will also look at some applications of nuclear physics, including fission and fusion. So radioactivity is also known as radioactive decay. It's a process in which an unstable nucleus emits any of three types of particles. So the idea can be shown with this diagram here. This kind of sums it all up. Here is our nucleus, and let's assume it is an unstable nucleus because it doesn't have the proper balance of protons to neutrons. So this nucleus is radioactive. So what does it do? Well, it is going to release one or more of three types of radiation. The first one is called the alpha, the second is the beta, and the third is the gamma. So the three types of radiation, or nuclear radiation, are alpha, beta, and gamma. So an alpha is named after what's called an alpha particle. And an alpha particle, it turns out, is a helium nucleus. So this kind of sounds strange, but remember what a helium nucleus is it's got two protons and two neutrons. So its notation is He for helium, and 2 down here is the number of protons, and then 4, remember, that's the total number of protons and neutrons. So since it has a total of 4 here, the 4 is up on top there. This helium nucleus is called an alpha particle, and this radioactive nucleus actually shoots this alpha particle out just like a gun would shoot a bullet. Another option or type of radiation is called beta radiation, and this is a beta particle. Now, a beta particle is also something very familiar. It's just an electron. So an electron, there's a couple of things to note here. First of all, the question, might come up, well, wait a minute, how does an electron come out of this nucleus? I thought the nucleus just had protons and neutrons. Well, you're correct. That's all the nucleus contains. But we're going to learn how an electron is actually produced by the decay of one of these neutrons, and so it can actually spit out one of these electrons. So this electron, or beta particle, let's talk about its notation here. So the E for electron, that makes sense. The 0 up on top makes sense because remember, the number up here is the atomic mass number, which is the total number of protons and neutrons. Well, an electron has no protons and no neutrons in it. Okay, the electron is this tiny little bit of negatively charged fluff or material. So it has 0 for atomic mass number. Now, the number down here is the number of protons, but really what this number down here tells us is the charge, the number of positive charges. In other words, the helium nucleus up here has 2 positive charges, 1 for each proton. Well, an electron has a negative charge, and the negative charge of the electron is the same as the positive charge of the proton, except of course the sign is flipped. So that's why we see a -1 down here for the electron. Okay, so the notation for electron is 0 on top, -1 on the bottom. Now, the third type of radiation that a unstable nucleus can emit is a gamma ray. This is just a photon, and this is actually light. But gamma radiation is a very special kind of electromagnetic radiation in that these gamma rays have very high energy, whereas visible light photons might have around 1 electron volt, maybe a couple electron volts of energy. Gamma rays can have millions of electron volts. So they are millions of times more energetic than regular light photons. However, it is still a photon. It's a little burst of electromagnetic energy. So these are the 3 types of radioactivity: alpha, beta, and gamma. One of the big differences between the 3 types of radiation, the alpha, beta, and gamma, is the penetrating power of this radiation. So for example, an alpha particle is more massive because it's got 2 protons and 2 neutrons, and so there you can think of them as kind of these large, clumsy particles compared to an electron or a photon. So an alpha particle is actually stopped very easily. Just a piece of paper or our skin is enough protection from almost all alpha particles. Sometimes they will get through maybe 1 or 2 layers of paper, but usually not. The beta particles, remember, these are electrons, and this is not drawn to scale. This electron would be extremely, very, very tiny compared to this alpha particle, and also very light. Okay, it would weigh almost 10,000 times less than this alpha particle. So this little electron is, you can think of it like a very tiny little bullet, and it's able to penetrate through paper or skin, but it can be stopped by something, for example, like a piece of foil or a thin piece of metal. Gamma radiation, on the other hand, remember, a gamma particle is a photon, right? It doesn't have any mass at all. It's just electromagnetic energy, and very high energy, and it can penetrate through just about anything. It'll go through into our bodies. It'll go through a brick. It'll go through a piece of armor, solid steel. It usually takes a thick lead block or a thick wall of concrete and steel to stop the gammas. So let's take a look at a couple of videos. You're first going to learn how an instrument called a Geiger counter works. The purpose of a Geiger counter is to detect radiation like the alpha, beta, and gamma. And then you'll see a demonstration of the radiation penetration.
What is a Geiger counter?
First developed in 1928 by doctors Geiger and Mueller, the Geiger counter was a device designed to determine whether or not an object was radioactive and emitting radiation, and to potentially count and determine how radioactive an object was. This rock we have determined to be radioactive using a Geiger counter. This rock does not appear to be radioactive. The Geiger counter has performed its most basic function. The basic function of a Geiger counter is incredibly simple. There is a gas-filled tube with low pressure. Electrical voltage is applied to one end, and on the other end, there is a ground. The electricity wishes to flow across, but it cannot do so because the gas by itself is non-conductive. When radiation, for example the cesium-137 source, approaches the tube, the high-energy particles entering the tube slam into the electrons in the gas. The electrons are discharged and knocked free, and they're pulled by the electromagnetic gradient, that is, the electrical field that makes the particles all want to move from one side to the other. They want to move from here, where the energy comes in, to here, where the energy leaves. As they are pulled across, they dislodge other electrons, creating an avalanche. That avalanche flies from one side to the other and is an electrical pulse which is recorded by the instrument.
Hi there, I wanted to do a quick demonstration to show the three common types of ionizing radiation: alpha radiation, beta radiation, and gamma radiation. And to do that, I've got a simple Ludlum Model 3 survey meter with a Ludlum Model 44-9 pancake GM detector attached. This type of detector has a thin mica window that allows alpha, beta, and gamma radiation all three to penetrate, so I can demonstrate all of them. So to start out with, I'll turn the audio on. I'm on the most sensitive scale, which is the 0.01 scale. You can hear the natural background radiation there. As I approach with this polonium-210 alpha source, alpha travels a very short distance, maybe a couple of centimeters, an inch or two in air. So you can see I've got to get really close, within an inch, before I can even detect that alpha radiation. If I hit the reset button here, I'll show it again. I've got to get right up on that detector before it starts to see that alpha particulate radiation. To demonstrate how easy it is to stop alpha, I've got a single sheet of paper that I'll slide in between the detector and the source, and you can see it takes a minute for that to fall back down to zero, but it's very easy to block out alpha radiation. Alpha is primarily an internal hazard. If you ingest or inhale material that emits alpha radiation, it comes in close contact with your body tissue and can cause harm that way. Outside the body, it's pretty harmless. It can't even penetrate the dead layer of skin cells on our body. To demonstrate beta radiation, I've got a beta source here, and you can see already several inches away it's giving me a reading, so I'm going to range up to the ×1 scale here and hit the reset button. But obviously the betas will travel farther than the alpha. I'm going to set that there. I'm going to grab my piece of paper and stick in here, and you can see that the paper doesn't do anything really to block that beta radiation. But something like a sheet of plexiglass, if I stick that in between there, that'll block it down and send it right back down to essentially background. So it's pretty easy to stop beta radiation. It'll travel maybe 10 to 20 feet in air depending on the energy of the beta radiation or the source that you've got. The last type of radiation I want to show is gamma radiation. I've got a cobalt 60 button source here, and it's not a real strong source, so I can't show you the distance that gamma is capable of traveling. If you have a strong source, these guys could travel hundreds of feet in air. But you can see here that what I can show you is the penetrating ability of this type of radiation. I can take again that piece of paper and stick in there, and it's not going to do anything at all. If I take the plexiglass and put in there, again, that blocked the beta radiation, that doesn't do anything. It really doesn't block it out at all. What we need to shield out the gamma radiation is dense material like lead, concrete, steel, things like that. If I put the lead, I've got some lead here that's wrapped in tape. I'll take a couple sheets of that and slide in there. Then I can range it back down to that ×0.1 scale. And you can see that was pretty effective in blocking out that gamma radiation. But gamma is very penetrating. I can put my hand here and it'll penetrate right through my hand. In fact, it will penetrate through the back, the metal back of the detector. So gamma is the one that's most penetrating. We typically use time, distance, and shielding, minimizing your time and maximizing your distance, and use shielding whenever possible to shield that. Okay.
Now that we've been introduced to the alpha, beta, and gamma radiation, let's take a look at each of these in a little more detail so we can actually work some problems with this. So the first one we're going to look at is the alpha radiation. So the process is actually called alpha decay. And what this means is we start with a radioactive element over here. In this example, it's this element, or this nucleus, is plutonium. In which plutonium has the atomic number of 94, and this one has an atomic mass number of 240. So what this plutonium does, since it's radioactive, is it spits out an alpha particle. Now remember, an alpha particle is a helium nucleus with 4 on top and 2 on the bottom. And what happens when this plutonium loses 2 protons is it's no longer plutonium, because this atomic number down here, number 94, changes to number 92 because it lost 2 protons. And atomic number 92 is not plutonium. In fact, it's uranium. So plutonium has changed or transmuted into uranium here. Now something else has happened. Notice the atomic mass number up here, which was 240, has to drop down to 236 because this alpha particle carries away 4 total, right? 2 protons and 2 neutrons. So we end up with uranium-236 as the product of the alpha decay. We started with plutonium, we end up with uranium and an alpha particle that gets shot out. So the nuclear reaction equation can be written as follows. So this is, sort of a picture showing what's going on, but here's the way we can write this as a reaction equation. On the left side is what we start with. We have plutonium-240, and it undergoes an alpha decay. So this arrow with a little alpha up there indicates we're undergoing a decay. And what we're left with are these 2 isotopes here. We have uranium-236 and we have helium. This is our alpha particle, of course. Now notice the math here makes this very simple. Down in the bottom we have 94 over here. Over here we have 92 plus 2, which of course is 94. Look at on the top, we have 240 over here. Notice over here we have 236 and 4, which add up to 240. So the way to do these reaction equations is to start with what you're starting with here, the plutonium-240, 94, and write down the helium nucleus, because it's an alpha decay, so we know we're going to have helium-42, and then figure out what these 2 numbers are here, and then we can look on a periodic table and determine what element it is. So go ahead and see if you can do this alpha decay practice problem. This is radium-226, which undergoes alpha decay. So see if you can figure out at least what the numbers would be here of the products over here on the right side. So go ahead and pause the video and work this out on some scratch paper. All right, so here's the solution to our alpha decay of radium. So what I'm going to do is this is what we start with. We were given radium-226-88, and it's going to alpha decay, so I'm going to have my arrow here. So on the right side, I don't know what I'm going to end up with, so I'm just going to draw an X over here. But what I know is that since it's alpha decay, I have helium-42. So now all I have to do is figure out what these numbers are. Well, remember, the numbers have to add up. So if I have 88 here and 2 here, I must have 86 on the bottom. Likewise, if I have 226 over here and 4 here, I must have 222 here. So my product here, the X, is element number 86. So I look down here in the table, and here it is, number 86. And this is Rn, which stands for radon, okay, which is a gas, a radioactive gas. So we have radon-222-86 plus our alpha particle here, our helium nucleus. Let's now turn to beta decay. So the question with beta decay, again, is remember what beta decay is we have a radioactive nucleus here that spits out a beta particle, which is an electron. So the main question is, where does this electron come from, since there are no electrons inside the nucleus? A nucleus is just protons and neutrons, of course. Well, the answer is that a neutron can decompose into a proton and an electron. So a neutron, N, can decompose, in other words, break apart and become a proton and an electron. All right, and so notice if we look at the nuclear numbers here, a neutron has no charge, so it has a 0 down here, and of course there's 1 neutron, so we have a 1 up here. A proton has a charge of 1. Okay, so there's 1 proton, so we have a 1 down there, and there's 1 proton, so we have a 1 in the top also. And then remember, we just talked about the electron. It has a negative charge, so it has a -1 down at the bottom, like the atomic number. And then on top, which is the total number of protons and neutrons, it's 0, because the electron is this tiny little particle that weighs almost 2,000 times less than a proton or neutron. So it doesn't really have any mass at all per se, so that's why there's a 0 up here. Again, notice the numbers all balance. A 1 up here, we have a 1 plus a 0 on the right side, so they add up. A 0 here is equal to 1 plus -1, right? The 1 and the -1 add together to get 0. So everything is balanced here in this nuclear reaction equation. So let's take a look now at what happens when this is radium-228-88. This will undergo a beta decay and form actinium-228-89. Now, how do we get this? Well, notice we started here with 88, and we have to get rid of an electron, which is -1. So this number over here must go up from 88 to 89, because remember that these two have to add together to get the original over here. So 89 plus -1 is 88. The 0 here means that this number 228 on top is not going to change. So that still becomes, that still remains 228. The last step then is to look up on a periodic chart what is element number 89, and it turns out it's actinium, which has the symbol AC. So let's write out the nuclear reaction equation. Instead of drawing this diagram, we can just write it out using the symbols. So here is radium-228-88. This arrow means it undergoes a decay, and it's a beta decay. All right, and we have, we're going to write down our beta particle, our electron, with a -1 on the bottom and 0 on the top. So what number goes down here? In other words, what adds to -1 to get 88? Well, it's 89, because 89 plus -1 is 88. So the trick is just whatever this number is here, it's going to always move up 1. It's going to go up by 1. The 228, as I just explained above, doesn't change at all because there's a 0 over here, okay? So here's a practice problem for you. Carbon-14 undergoes a beta decay. What are the products over here on the right side? So again, go ahead and pause the video and figure out what the numbers would be. Start with this over here, figure out what these numbers are, and then we'll look on a periodic table to finish the problem. Okay, so our solution for the carbon-14 beta decay is, I'm going to write carbon-14, 6, becomes some unknown X plus an electron. This is our beta particle with a 0 on top and a -1 on the bottom. So the numbers, remember the 6 down here must go up by 1 to 7, because 7 and -1 have to add together to get 6. The 14 on the top stays 14 because of the 0 over here. So the last step is to figure out what is element number 7, and we look on the chart and we find that element number 7 is nitrogen. So here is our final nuclear reaction equation for the beta decay of carbon-14. Before we talk about gamma decay, I should just mention that when you take the quiz, it's probably a good idea to have a periodic table of the elements handy. Either make a copy of one, make a printout of one off the internet, or if you have your textbook, you can have your textbook open or another book. But it'll be helpful to do the decay problems. So the last one we're going to look at, we've already looked at alpha and beta decay. Let's look at gamma decay. Now, what is a gamma decay? Well, a gamma decay occurs when an excited high-energy unstable nucleus emits high-energy photons to reduce its energy. So what happens in a gamma decay is we have, let's say we start with plutonium-240-94. And this, you can think of this nucleus here in an excited state. Now, what does that mean? Well, we can think of the nucleons inside here have too much energy, and they're jumping around too much, so this thing is unstable. So the way this thing can actually stabilize itself is just by spitting out some high energy gamma particles. All right, these gamma rays or gamma radiation, remember, they're just photons. They're electromagnetic waves. And these photons typically carry millions of electron volts in energy. So they're extremely high energy, actually very dangerous, especially in higher doses. Gamma rays they can be lethal. So what happens here, since a photon has no charge, it has no protons, no electrons, and no neutrons, it's something completely different, right? It's a photon. It's a little bundle of energy. This original nucleus doesn't change at all right? It still is plutonium-240 and 94. None of the numbers change. The reason for this is our gamma particle, this is, the Greek letter gamma there, has a 0 on the top and a 0 on the bottom. All right, no charge, no mass. So in order to balance this equation, the 240 stays 240, the 94 stays 94, and since the atomic number, 94, didn't change, it must still be plutonium. So a gamma decay reaction equation is somewhat trivial. We have whatever we start with, we end with the same thing plus a gamma particle. So here's a practice problem, just so you can say you did one. Here is suppose this radium-226-88 undergoes a gamma decay. What would we have on the right side? Okay, so I'm assuming you did this maybe just in your head. Obviously, all we're going to have on the right side is this same radium-226-88, plus we're going to have one of these guys, a gamma particle. With the 0 and the 0, and those are our two products. One of the concepts that has to do with radioactivity is the idea of half-life. And the actual study of half-life comes from statistics. And the reason for this is that when we're talking about radioactivity, it's very difficult, or it's basically impossible, to predict when any given nucleus will undergo radioactive decay. In other words, it might be a second from now, it might be tomorrow, or it might be in 1,000,000 years from now. It depends on what is called the half-life. And so this is a statistical method of basically determining how long a radioactive substance will stay radioactive. So the half-life, or T1/2, is defined as the time it takes for 50% of a sample of nuclei to decay. You've probably heard the term half-life before. They use it when they talk about drugs in our body. For example, caffeine has a half-life of, I want to say something like 4 hours. I might be a little off there, but let's just assume that caffeine has a half-life of 4 hours. So what does that mean? Well, that means when you drink a cup of coffee in the morning, you get that full dose of caffeine. Okay, let's say it's 30 milligrams of caffeine or something like that. Well, with a half-life of 4 hours, what that means is 4 hours later, your body has eliminated half of the caffeine. So you still have half left. It's as if you still have half a cup of coffee in your system. Now, another 4 hours later, meaning 8 hours total, we have half again in our body. So now, that original cup of coffee that we had in the morning first gets cut in half. Now we only have 1/4 of that cup of coffee left 8 hours later. And then let's go another half-life. Another 4 hours would be 12 hours after you drink that coffee. That quarter cup of coffee is now down to 1/8 of a cup. So, after something like 3 half-lives there, after 12 hours, there's very little caffeine left in your body. And, obviously you're not going to really have the effects of that coffee anymore, which is a good thing because you want to get to sleep at night. So anyway, this is sort of the idea of half-life. It's the time it takes to lose 50% of what you started with. So let's look at an example here. Iodine-131 this is an isotope of iodine, which is an radioactive element. And it beta decays into xenon-131 with a half-life of 8 days. Okay, so here's the reaction. Iodine-131-53 undergoes a beta decay to become xenon-131-54 plus here is our beta particle. This is the radiation, right? This is the beta or electron that's kicked out as a radioactive particle. So this reaction here has a half-life of 8 days. So what does that mean? Well, suppose we start with, let's pick a nice round number here that we can easily divide by 2 many times. So let's start with 64,000 nuclei of iodine-131, okay? So at time 0, we start with 64,000 iodine. And obviously we haven't, started the clock yet, so we haven't undergone any half-lives. We're at 0. And so we have the full fraction remaining. In other words, all of those 64,000 are still iodine. Now, 8 days later, okay, remember that's the half-life, 8 days. So after 8 days, 64,000, we're down to 32,000. So after one half-life, we're at 1/2 of the remaining number of iodine nuclei. After 16 days, now we've undergone another half-life, so that 32,000 gets cut in half to 16,000. So at 2 half-lives, we're at half of 1/2, which is 1/4 of the remaining amount. Okay, 1/4 of what we started with is left. After 24 days, or that's 3 half-lives, this 16,000 gets cut in half to 8,000. All right, or we're at 1/8 of what we started with. After 32 days, that's 4 half-lives. We're down to 4,000, or 1/16. After another half-life, we're down to 2,000, right? And then 1,500. You can see each half-life, we just keep dividing this number by 1/2. That's the meaning of half-life. And the fraction remaining is a multiple of 1/2. So here we have 1/2, 1/4, 1/8, 1/16, 1/32. We just keep multiplying by 1/2 each time. And this is what a graph of this process would look like. And this is plotted, this is the number of nuclei here versus the time in half-lives. So after 1 half-life, we're at 1/2. After 2 half-lives, we're at 1/4, 1/8, 1/16, so on. And then finally, once you get over here to 7, 8, 9, 10 half-lives, you're at a very tiny fraction of what you started with. So here's a half-life example problem. Suppose a radioactive isotope has a half-life of 8 years. What fraction of a sample of this isotope will remain after 24 years? So our answer, let's first determine how many half-lives take place during the 24-year period. Well, all we do is take 24 and divide by 8. That's 3 half-lives. So we're going to have to deal with 3 half-lives. So step 2, we're going to determine the fraction remaining after 3 half-lives. Well, each half-life, we cut it by a factor of 1/2. So we have 1/2 times 1/2 times 1/2, which is 1/8. That's how much remains after 3 half-lives. The other way to do it, kind of a shortcut, if you like using exponents in math, you just take 1/2 and you raise it to the 3rd power, because we have 3 half-lives. So 1/2 to the 3rd power, which is 1/2 times 1/2 times 1/2, is the same as 1/8. There are thousands of known isotopes that are radioactive. And interestingly, the half-life depends and varies widely. There's a huge range of half-lives. So look at some of these values here. There's an isotope of helium, helium-5, that has a half-life which is 10 to the minus 21 seconds. This is something, on the order of a trillionth of a second. In fact, this half-life is so short that you'll never find any helium-5 laying around anywhere because it's going to decay so quickly. Helium-8 has a half-life of about 1/10 of a second. Carbon-15, now we're talking about 24 seconds. This is silver-108, has a half-life of about 2.5 minutes. Uranium-237, about 7 days. Carbon-14 is 5,730 years. And look at this one, uranium-238 has a half-life of about 4.5 billion years. So obviously, uranium-238 is much more stable than helium-5. because helium-5, every trillionth of a trillionth second, it's going to basically decay, leaving only half of what is left. For uranium-238, it takes 4.5 billion years to lose half of our original sample, meaning this is going to decay much, much more slowly. So there's a huge range in half-lives. Another interesting application of nuclear physics is the concept of radiometric dating. And this is a method that's used by geologists, archaeologists, physicists, and even astronomers to measure the age of rocks or artifacts, including meteorites. So the way this works, and again, we won't worry about too much about the details here, but this is sort of a hypothetical example. Let's suppose that we have a rock, and when it forms in the earth, it has some collection here of radioactive uranium isotopes, okay? And let's just suppose, to make the math easy, that this particular isotope of uranium has a half-life of 1 billion years. So what that means is 1 billion years later, if we were to pick up this rock, we would find that only 1/2 of those uranium atoms are left. What happened to the other half? Well, they underwent radioactive decay, and they decayed into something different. In this case, it looks like it's lead, Pb. So we have half lead, half uranium. Now, after another billion years, all right, so after 2 billion years, if we were to find this rock, we would notice that the uranium is now only 1/4 of the original, because we lose 1/2 and 1/2 again. And 3/4 is the blue lead atoms. And then let's go one more half-life. So after 3 billion years, all that's left from the original population here of uranium is 1/8 of the original number. The other 7/8 are all lead. So suppose we take this rock into the lab, and we don't know how old it is, but we notice that there is 1/8 uranium and 7/8 lead. Well, we can therefore assume, and correctly assume, that we have undergone 3 half-lives, because that's what happens. That's how we get to 1/8. We go 1/2 times 1/2 times 1/2. We do that 3 times, we get to 1/8. So if we know what the half-life of this uranium isotope is, and we do, we know it's 1 billion years, we can now safely determine the age of this rock at 3 billion years. So this is a very powerful method, and I've kind of oversimplified it here, because what they actually do is they look at a bunch of different radioactive isotopes. They don't just take one like this. They take a whole collection of them, and they basically make sure that the results are consistent with each other. They should all show a similar age for when that rock was formed. And this is how scientists get extreme confidence and precision in dating the rocks and figuring out when they actually formed. So one kind of interesting bit of information that comes from this is that the maximum age of rocks found on the Earth, the Moon, Mars, and more importantly, the meteorites in our solar systems are always found to be less than or equal to 4.6 billion years. This is the age of our solar system. We know our solar system formed about 4.6 billion years ago, and the way we know this, one of the pieces of physical evidence that supports this is this use of radiometric dating of meteorites and other rocks. Let's now turn to an amazing phenomenon called nuclear fission. It was discovered a while back, almost 100 years ago now, that if you took a uranium nucleus, which is a big nucleus, all right, it has 92 protons, and it has about a total of 238 total neutrons and protons. So this is a big nucleus, big ball of neutrons and protons. If you take a neutron and shoot it into this uranium nucleus with a lot of energy. Okay, think of this like a high-speed bullet that flies into this uranium nucleus. Something amazing happens. The nucleus deforms. It actually kind of starts to spread apart from the collision. All right? You can think of this like a lump of jello. And when you throw something into the jello, the whole thing wiggles. And so it sort of stretches out. And once these two lobes here on each end get far enough apart, remember the nuclear force doesn't work over a long distance. So this part of the nucleus up here is no longer attracted to this part down here. Instead, they're repelled from each other from all these positively charged protons. So what happens is this nucleus actually splits into two pieces. These are called the daughter nuclei. This is the parent nucleus here, and these are the two daughter nuclei. And in addition, there will be some smaller fragments. These are some extra neutrons that just sort of, flew off of when this thing exploded like this. There are some extra pieces that fly off. Now, there's a couple of amazing things about this process. First of all, nobody knew that a nucleus, you could actually split an atom like this, right? The other thing is that this whole process of the neutron flying in here, making this thing shake and vibrate until it snaps into two pieces, this whole process only takes on the order of a trillionth of a second, which means it's practically instant. So nuclear fission is the splitting of a large nuclei or nucleus into smaller fragments. And in the process, it's going to release a large amount of nuclear binding energy. Remember, that's the energy that binds all these nucleons together. Now, here's what's amazing about the energy of this thing. When one of these uranium nuclei breaks apart or goes into fission here and snaps into two pieces, it releases on the order of 200 million electron volts. Now compare that to a chemical reaction, for example, burning coal or gas or any kind of natural gas, gasoline, any kind of fossil fuel, usually releases about 5 electron volts per chemical reaction. Here we have a nuclear reaction that releases 200 million electron volts. That means this nuclear fusion reaction is on the order of 40 million times more energy than burning coal. So this is the great promise of nuclear energy. The energy source, it has tremendous potential because there's so much energy trapped inside this nucleus. The way this energy can be harnessed, obviously just having one uranium nucleus undergo fission is not going to release that much energy. But what happens is we can actually have a chain reaction, a sustained chain reaction. And the way this works, remember our process here. The one neutron flies in here and it hits this uranium and it breaks the uranium into two fragments. Let's suppose this fragment is krypton and this fragment is barium. Okay, these are two fairly common fragments of uranium fission. Well, remember that there's also 3 neutrons were liberated or released in this when these things broke apart. So these 3 neutrons now come flying out. They can hit 3 more uranium nuclei. Each of these uranium nuclei is now going to split into krypton and barium, krypton and barium, krypton and barium. And in each of these fissions, we're going to release 3 more neutrons. So now we've got a total of 9 neutrons here released. All right, after just, this is just the 3rd generation here. And each of these 9 neutrons can slam into 9 more uranium nuclei. And you can see how this process is building up very quickly. And remember that each generation from here to here, and then from here to here and here to here, only takes a trillionth of a second. So within a very, very small fraction of a second, we can have many, many, many generations of fission reactions going on, which is a chain reaction. It's sort of a self-sustaining reaction that builds up with time. Now, the ability to sustain a chain reaction requires a minimum amount of fuel in order to capture all these neutrons. If we only have a tiny little speck of uranium, a lot of these neutrons fly out of the sample and they're not caught at all. They don't create more fission. So we have to have a minimum amount of fuel, which is called the critical mass of fuel. The original application of nuclear power and energy was actually to build nuclear weapons during World War II. But after that, it was also realized that the nuclear power could be harnessed to produce electricity. And so as a result, there are many, many nuclear power plants throughout the world that supply electricity, basically. And to learn how a nuclear power plant works, it's actually not that complicated, at least on the outside. What we have here here's the nuclear fuel rods here, and the rate of chain reaction in here is moderated by something called a moderator. And the moderator basically absorbs those neutrons to control the speed of the nuclear fission reactions. So within this this nuclear fission reactor here, we're generating a lot of heat. All this energy is being released, and it basically heats up a high pressure water here often. That is, since it's under high pressure, it stays at a liquid, but it's superheated, and it is pumped through this steam generator here. But notice the water that actually comes in contact with the fuel rods is contained here and doesn't escape. It just circulates through this system here. The main idea here is we just want to generate heat to boil the water in the steam generator and create steam. That steam then drives a turbine, a steam turbine, which is connected to an electric generator, and this generates electricity. The steam then is cooled and condenses and goes back into the steam generator here. And this is done, using other water, cooling water, to cool down the steam. So nuclear power plants, they're somewhat controversial because they have both advantages and disadvantages. The advantages of nuclear power are pretty straightforward. There's two of them. The first one is the efficiency. Remember that a nuclear reaction is 40 million times more powerful than burning coal or fossil fuel. So in other words, instead of needing a whole train full of coal, you can just use one small pellet of uranium. Okay, so incredibly efficient. The other nice thing about nuclear power is that there are no carbon dioxide emissions. The nuclear reactions that are going on in here release no carbon dioxide. All right, we're not burning anything. We're not burning coal. We're not burning oil. We're not burning gas. So in terms of greenhouse gases, okay, in terms of climate change, nuclear power plants are extremely safe in that sense. We're not adding carbon dioxide to the atmosphere. However, I guess there's no free lunch here. There are some severe disadvantages to nuclear power. The one is that these fuel rods here have a limited lifetime. Once the uranium all undergoes fission, it's turned into byproducts. And we saw krypton and barium. The problem is those byproducts are very radioactive. They don't have the right ratio of protons and neutrons, so they are radioactive. And the problem with this waste, this radioactive waste, is what do we do with it? And one of the reasons that's a problem is because the half-lives of these spent nuclear fuel rods can be thousands of years. So remember what the half-life means, right? In 1,000 or 5,000 years from now, these spent fuel rods are still radioactive and very dangerous. So even if we, pack these things away and put them in barrels and bury them in a cave somewhere, hundreds or thousands of years from now, those barrels may deteriorate and this radioactive waste can leak out. So the question of what to do with the waste is a big downside to nuclear power. The other big one here is safety. We're talking about nuclear reactions here with a lot of radioactivity, so it's dangerous not only to those that may be exposed that are working in the power plants, but every once in a while we've heard of some horrible disasters with a nuclear power station that undergoes either a meltdown or a leak. The ones that come to mind are the worst by far was the one in Russia at Chernobyl, and you can look that up if you're curious about what happened there. But it was awful. It basically poisoned a whole community and area around it with deadly radiation. In the United States, we had a pretty bad scare back in the 1970s at a nuclear power station called 3 Mile Island, and there was a near core meltdown there too. And then more recently, there was a big earthquake off of the coast of Japan, and the reactor in Japan suffered damage and cracks, and some of this radioactive steam escaped from the reactor. So the safety is a huge concern with nuclear fission reactors. Sort of the opposite process to nuclear fission is called nuclear fusion. So nuclear fusion is combining two small nuclei to form a larger nuclei, and this also releases a huge amount of energy. In fact, nuclear fusion is 4 times more energetic than fission by weight. So the idea of fusion is you take 2 light elements, nuclei. These are 2 hydrogen isotopes. This is called deuterium, or heavy hydrogen, H2. And they will, under the right conditions, you can fuse these together to form helium. And it releases a high energy neutron and a lot of energy. This is a deuterium tritium fusion reaction where you have deuterium, which is H2, and tritium, which is H3. These are 2 isotopes of hydrogen. They can fuse together. This is actually the reaction that is used in the hydrogen bomb, the fusion bomb, and it fuses together and releases a tremendous amount of energy. You can see this neutron is kicked off with 14 million electron volts of energy, and this alpha particle has about 3.5 million electron volts of energy. Now, fusion is interesting because it is potentially a source of very safe, very clean nuclear energy. It doesn't have the same problems that fission has regarding waste, radioactive waste, and so forth. In fact, if fusion could be done, and they're working on it right now, there would be an unlimited supply of basically very cheap energy for the world. In fact, I've heard that you could take a water bottle full of ocean water, go down to the beach, fill it up with seawater, and that would power your whole house for over a year. All right, so there's a lot of great promise here. The difficulty is the technology and the engineering required to get a fusion reaction to be sustained and controlled. And let's look at the physics of this real briefly. We're trying to fuse 2 hydrogen nuclei together. In other words, 2 protons. But 2 protons, of course, they don't want to come together because they're both positive charge. So there's an electrical force here and here pushing these 2 protons away from each other. Remember, the nuclear force is much stronger than the electrical force, but it only acts in this little region around the proton. The nuclear force, remember, has short range. Even though it's 100 times more powerful than this electrical force, we can't get these protons close enough together so that these regions of nuclear force overlap. So the way to do this, though, is we can use high temperature. Remember that when we heat up a gas, the gas particles move around faster. So if we can heat the hydrogen gas to more than 5 million degrees, these protons are going to have enough speed to actually overcome their electrical repulsion. So once the protons get close enough together here like this, because remember they're flying towards each other at a really fast speed, then once these ranges of nuclear force overlap, these two protons now can feel each other, and the attraction here, due to the strong nuclear force, is 100 times more powerful than the electrostatic repulsion. So these two protons now slam together with full force of the nuclear force, right? And this releases a huge amount of energy. And so this is what fusion is all about, forcing these protons to get close enough together so that the nuclear fusion force, strong force, can take over and fuse the two protons together. Now, that sounds easy enough on paper. All we have to do is heat up the hydrogen gas to, something like 5 or 10 million degrees. But here's the technological problem. There is no material that can withstand those temperatures. In other words, you can't have a container made out of metal or diamond or ceramic or anything you can think of. You can't have anything that won't boil away at temperatures just in the few thousands of degrees. We need to get up into the millions of degrees. So there's no physical way to contain the reaction. So how do we do it? Well, there's two ways to do it. Nature does it very interestingly. This is the way stars work. Here's a picture of our sun. In nature, gravitational confinement is used to confine the fusion reaction. Now, how does that work? Well, you have to have something as big as a star, and this star is, you could fit 1 million Earths inside of our sun. So this is a giant nuclear fusion reaction chamber, but it's obviously we can't build something like a star. All right, but this is one way to confine the fusion reaction, is to have gravity squeeze all this gas together and heat it up. The center of our sun is about 15 million degrees Celsius. That's well hot enough to create fusion, and that's what powers our sun. The other way to do it, the man-made way to do it, is by using magnetic confinement. And what they do is basically the fusion reaction exists in this sort of donut-shaped cavity, and there are super powerful superconducting electromagnets that confine the hot hydrogen plasma, which is basically a charged gas, and it keeps the fusion reaction confined, not physically but magnetically. And this is something that's being worked on at General Atomics right here in San Diego. The hope is that within the next couple of decades, we might have commercially viable fusion reaction to produce electricity. Just a couple more slides here. Another interesting application of fusion reaction that occurs in nature, and this is something we'll talk about when we study astronomy in the last part of our course, but the formation of the heavy elements they were all the elements in the periodic table except for hydrogen and helium basically are created inside of stars by nuclear fusion. So in other words, a star starts out as just a big ball of hydrogen gas, but inside the core of the star, where the temperatures are really hot, the hydrogen is squeezed together and fuses to form helium. And this is what powers our sun. Later, the helium can fuse together to form carbon, and the carbon can fuse with helium to form oxygen, and so on and so forth. So this process just keeps going. And within a star, during its life and death, all of the heavy elements in the periodic table are actually created inside the core of a star by nuclear fusion. So this is kind of a fantastic fact that we have learned about astronomy and about where the heavy elements come from. All of the atoms that are in our body and that make up our Earth and our buildings and our houses and our cars, they were all manufactured naturally inside of a star. And there's a famous saying by an astronomer named Carl Sagan. He said, we're all stardust. We are what's left over from a star that blew itself up. This is a picture of an exploded star called a supernova. And all of this gas that's been returned to the universe is enriched with all the heavy elements. So in other words, the iron in your blood, the calcium in your bones, the carbon in your DNA, all of that in your body was once inside of a star. So it kind of is an amazing cosmic connection between us and the universe. We'll look at this in a little more detail later on in the course when we study the life and death of stars. The last slide here in our chapter, I just want to real briefly touch on the subject of nuclear weapons. Historically, nuclear weapons, it's kind of an amazing story. This was actually the first application of nuclear physics. And you know, the story of the atomic bomb development during World War II, it was basically a race between the United States and Nazi Germany to see who would develop atomic weapons first, because whoever got them first was basically going to win the war. So there are two types of nuclear weapons. The one uses fission, nuclear fission, which remember is splitting apart of the atoms or the nuclei, and these are usually called atom bombs. The other type of weapon uses the fusion reaction, and this is called a hydrogen bomb. So just real briefly, in the fission bomb, the way they work is there are a couple different ways to do this, but they take two subcritical masses of fuel, either usually uranium or plutonium, and they combine those two. Now what I mean by, remember, subcritical means these pieces are less than the critical mass needed for a reaction to occur. But when they're combined together, they now become supercritical, meaning they're more than the critical mass needed. So one way to do this is they actually shoot, using a cannon inside the bomb, they shoot one piece of uranium into a target piece of uranium, and when the two of them combine, they become supercritical, and that starts the reaction, and within a tiny fraction of a second, the whole sample of uranium explodes. Now, what's amazing, again, about the power of nuclear materials is that a chunk of uranium about the size of a baseball, something you could hold in your hand, is enough to demolish an entire city. So we're talking about extremely powerful weapons here. These, by the way, were the only type. This is so far, fortunately, the world has only seen two atomic weapons used, in actual battle, and those were the ones that were dropped on Japan that ended World War II, and they were both fission bombs like this. The other type of bomb that was developed after the fission bomb was the hydrogen bomb, and these were developed in the Cold War. The United States and the Soviet Union made thousands and thousands of these bombs, and the fusion bombs are, unfortunately, much more powerful than the fission bombs. And these bombs, some of these can destroy an entire city, like New York City, with just one weapon. The way these work is they actually use a fission bomb like this here as what's called a primary, or a trigger, that starts the fusion reaction over here, and the secondary reaction here is a fusion reaction, which basically is fusing isotopes of hydrogen like tritium and deuterium. They fuse together and basically release a huge amount of energy. All right, so that, my friends, is our study of nuclear physics. We will change gears now in this course, and we will be talking about astronomy, so I will see you in the next chapter.